back squat is a fundamental strength movement that is performed through the sagittal plane and is used to develop both the knee and the hip extensors, as well as the plantar flexors. In the back squat, there are two major phases. These being the descending phase, also known as the eccentric phase, and the ascending phase, also known as the concentric phase. Furthermore, the ascending phase can be broken in subphases that see a change in both movement velocity and changes in muscle activations. These subphases are known as the acceleration point. This occurs between 52 and 80 degrees of knee flexion. The sticking region. This occurs between 80 and 110 degrees of knee flexion. The max strength region. This occurs between 110 and 127 degrees of knee flexion. And finally, the completion phase. This being between 127 and 180 degrees of knee flexion. It should be known that these values are subject to change among individuals due to different limb lengths, relative muscle strength, and mobility requirements. In this analysis, I'm going to focus on phase 1, the acceleration point. We see that in the acceleration point, the agonist muscles are going to include the plantar flexors, primarily being the gastrocnemius muscles, the knee extensors, being the vastus medialis and lateralis, and the rectus femoris, and last but not least, the hip extensors, the gluteus maximus, semitendinosus, semimembranosus, and biceps femoris. We now know that as well that depending on the depth of the squat, we see changes in the muscle activation. For example, if the peak knee flexion is 60 degrees or greater, we see an exponential increase in vastus medialis and lateralis activation. This being from approximately 78 up to 86% of maximum voluntary isometric contraction, while the gluteus maximus experiences a decrease from 83 down to 71% of maximum voluntary isometric contraction. Throughout the back squat, we see the bar resting on the trapezius muscle, with the grip being just outside shoulder width or wherever is comfortable for the individual depending on shoulder flexibility. A neutral spine should be maintained, and in the bottom position the weight should be evenly distributed throughout the foot. Looking at the acceleration point, there is an ankle angle of 62 degrees, a peak knee flexion angle of 49 degrees, and the hip angle is 41 degrees. Furthermore, the trunk creates a segment angle of around 55 degrees, whilst at the thigh and shank there are segment angles of 10 and 62 degrees respectively. Continuing on to the movement kinetics. As we accelerate out of the bottom of the squat, the anterior thigh muscles, vastus medialis, vastus lateralis, and rectus femoris create a knee moment arm of 3.4 centimeters, producing 19.9 newton meters of force. The posterior thigh and hip muscles, gluteus maximus, biceps femoris, semitendinosus, and semimembranosus, create a hip moment arm of 28 centimeters, thus producing 164 newton meters of force. And at the ankle, consisting of a 20 centimeter moment arm, the posterior shank muscles, the gastrocnemius and soleus, produce 117 newton meters of force. Meanwhile, the trunk muscles, such as the erector spinae, external obliques, rectus abdominis, and quadratus lumborum, contract isometrically to stabilize the trunk and maintain a neutral spine. Now we will look at the effects of wearing a weightlifting style shoe on both the kinetic and kinematic variables. Weightlifting shoes are often used to create a more upright torso and squatting movements. This is achieved through elevating the heel, thus reducing the foot segment angle by about 6 to 8 degrees. In addition to this, we see a further increase in peak knee flexion going from 49 to 44 degrees. It has been noted that there is a direct correlation between increased peak knee flexion and knee extensor excitation. In contrast, we see a decrease in the activation of the posterior thigh muscles, this reflecting the length-tension relationship. In this example, the ankle moment arm is increased to 22 centimeters, therefore producing 129 newton meters. The knee moment arm changes to 6 centimeters, increasing the applied force to 35 newton meters. And finally, the hip moment arm stays consistent at 28 centimeters, still producing 164 newton meters of force. Coaches and athletes can use such findings to target sport-specific movement patterns and focus on making adaptations to develop the anterior thigh muscle strength through increased range of motion. To conclude, we'll assess the use of a weightlifting belt and the effect it has on the trunk musculature and midline stability in the squat. Weightlifting belts are often utilised when squatting at relatively heavier loads and percentages. When looking at EMG results, there is a decrease in external oblique activation. Conversely, however, we see a significant increase in rectus abdominis activation. This is due to the feedback mechanism of the belt and the muscle having something to produce force against. In addition to this, utilisation of the belt and Valsalva manoeuvre sees a significant increase in intra-abdominal pressure. This is extremely important for decreasing risk of spinal injury as it reduces compressive forces and limits overall trunk motion under load.